the discussion on number system for digital system. In this, we missed this number system octal, where we would like to consider octa means r equals to a value 8 there. Now, with the same expression for a number n, if I express a number dn r to the power of n plus dn minus 1 r to the power n minus 1 till d0 r to the power 0 plus d minus 1 r to the power minus 1 d minus n r to the power minus n, in which this r is 8 there. Now, if I ask you what is this dn values can take in this number system, where we are talking, it is about a octal number system where r is taken 8. What are the possibilities? Obviously, it should be 0 to 7, not more than that, where 8 different numbers are there to represent the number. Let us say one number n is represented in octal number system. Let us take the example of one number 446.548, where this 8 represents this r value 8. And we can make the observation here that all the numbers which are used here, nobody has gone beyond this 7. Okay. Now, if this number we want to represent in decimal form or in decimal number system, where r is 10, that is why this 10 has come into picture there. So, now if I want to convert this octal number to decimal, how do I do? I follow the same path there, where I will find here n value which is found after point, I am saying 0, 1, 2. Small n is 2 for this, that means d2 is 4 into r means 8 to the power 2, r to the power of n, where n is 2 for this coefficient 4, then plus another 4, where again r 8 and n is now 1, n minus 1 it is, then 6 into 8 to the power 0 plus 5 into 8 to the power minus 1, 4, 8 to the power minus 2. Done. Now, please express it. 4 into 16 means 256. 4 into 64, 256. Then minus 5 by, okay, how much it is coming? I think 0.625 plus 0.0625 is supposed to come. Then finally it is coming 2946875 in 10. Okay. Let me remember the previous thing what we did for converting this decimal number into binary, or today we will be considering decimal number to octa. So, in that case, if this would be available to me, what I would do? 294 would be divided by 8. How much it is coming? I think 3. Is it right? Then 6, then 8, 4, remainder is sorry 4. So, what root should I take? Like this, that is why it is given there. Okay. Similarly, for after point 0.54 into 8, 0.54 into 8, how much it is coming? 4 point, oh, no, 0.6875 into 8, it is coming 5.5, carry is gone 5.5 into 8 equals to 4.0, so it is 4. So, I have to go down 5.4. The same technique what we used. Okay. So, that way decimal to octal or octal to decimal conversion you do. Fine. But why we consider decimal number? Because it is a actual value in the physical world what we face. Now, to represent it in our computer, which is a digital system, we represent them in binary form, where only 1 and 0 will be there. How come this another number system is coming into picture? That may be a question. Okay. You will get that idea why this kind of number system is also popular for our digital systems. See there, if one number, decimal number of this is represented in octal form here. Now, if I make this octal number into binary, how do I get? Let us see. If I say it is an octal number system, that should be represented by only either 0 or 1, so that I get the binary number. Okay. Now, if it is so, first I have to think how many variety of it should be there in my that language by which I want to present the octal number which is given here to my computer in terms of 1 and 0. Okay. This is the first question. Then I will see that here, since it is r equals to 8, so I have to represent 0 to 7 different sequences, so that all will be individual, so that I can represent something by them. So, 8 different levels I have to define there. Now, if I want to represent 8 different levels by using only 2 options, either 1 or 0, on or off. In that case, I have only 2 options and I have number of levels 8 there. So, I need to use at least 3 bits to represent the 8 different levels there, so that I can make 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 2 up to from 0 to 7, so that 8 levels are there available with me, so that all the stages which were used to represent this octal number system, them I can give the name of this kind. Some is 0, 0, 0, some is 0, 0, 1, some is 1, 1, 1, some is 1, 1, 0, like that. So, it is possible for me. Okay. With that idea, we will represent this number in binary form. For that, what do you need to do? You have to represent this 4 first. Which way? In terms of 3 bits. So, in this, if you like to get 4, how you will get? 1, 0, 0. Put that 1, 0, 0. Okay. Now, another 4, 1, 0, 0. Then 6, 1, 1, 0, 1, 1, 0, done. This part is done. Then put the point. again 5, 1 0 1. Your decimal, your binary number is now there. How? Yes. 3, this 3, this 3. Yes.
Does the computer actually understand in octal language or in binary language only?
It understand only, the question is that does the computer understand octal language or it understand only binary? I will say only binary. From my layman understanding, I will say my computer doesn't understand other than 0 and 1. Because my electrical systems, they understand only switch on and off, these two status. Now, if I make some another arrangement where I will ask him to check not only one place to see whether it is 0 or 1, whether it is switch on or off, I will ask him to check at least 2 or 3 bits say. If all are 0, then 1 you should understand. If all are 1, you should understand another thing like that. That means depending on 0 and 1 only, depending on switch on and off only, I am defining to my computer to understand. Okay. But if you say what computer understand, only 1 and 0, nothing else. Remaining thing you are developing. Just like for example, I will give. Initially, when computer started understanding the languages, you will see previous languages which were there, they were at the beginning, just like microprocessors and all. In that, we don't give any language like you write in your C or MATLAB. Those are very much user friendly. But at the beginning, we had to give this kind of numbers to the computer, to the processor, so that processor understand that. Because I have to give in a particular fashion, so that computer will read them and they will decide what I have to consider for this kind of combination there. So this language is provided by me to the computer. Okay. Why I am saying this is understand only 1 and 0? Because I am restricting my things to put to the computer in terms of 0 and 1 only. And remaining things are my organization or the way I am speaking. Which way people will understand, that depends on language to language, just like English, Hindi, Uriya. You are conveying the same message, but in different format. So it is not required that one computer who doesn't understand this kind of arrangement, it means it is not a digital system. Some digital system may be there that doesn't have those combinations there to give to him to understand this kind of arrangement of the binary bits. Okay. So these are the techniques we follow so that our all processors will be designed accordingly and it understand the language which we want to, with which we want to speak to the system. Okay. So this way. So this octal number system has this kind of options there where you need to take the number directly, make a digital binary conversion of it and put one after another. In that case, you will get the actual number itself. This is the usefulness of this octal number system in the computer. If you say please run in octal number system, then it will bunch the things in terms of this 3 and proceed. Okay. Let us take one extension of this, just like one small example from binary to octal. So this is the number given to me as binary number. I need to represent in octal system. Just another way, I will start from here because this is the point given there. So let us start from here, this 3 bit, then this 3, then this 3. Okay. If somebody simply keep here another 0 here or 1 here, in that case you should fill the blank there where you should able to make all as 3 3 3, just like another one has put, somebody has put here. So you put another 0 there left hand side, so that it become again a bunch of 3. Okay. Now if it is given in this fashion, make them bunches of this 3 and simply put them. This is 5, then 6, then 3, then 5, 2, 6. You are done. Okay. Let me extend it for hexadecimal. Yes.
So if there are only 5 digits, then
Where?
and after the decimal place, if there are odd number of digits, then
Still you can put 1 0
where to place the 0?
at the end. Always you are there to, you are having a option there to make 0 either in the left hand side or in the right hand side. You put it, it hardly matters because 0 into something. Okay, but if you put 0 in the other side, it means different actually, because this bit is getting one shift where n value is getting increased there. Okay, this is the reason. So, again I will follow the same route. 16, if I am talking about hexa, R should be 16. Now, how many options I will have? 0 to 15, but how to represent them? Yes. So, options are there till 0, 1 up to 9. It is fine, because in your decimal that is the highest number, 10 options are there from 0 to 9. Now, in this it asked more than that. We did not face any problem in octal system because it was less than 9. So, comfortably we put that. But here if it is there, let us name it in another way. Let us name next to this 9, which is supposed to be 10, is as A, and continue. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is C. See, total 16 options are there with you. So, when you represent a hexadecimal number into decimal, in that case if A is coming there, put the D value as 10. If F is coming there, put D value as 15. Things are done. Okay? This for the understanding. Now, let us take one example of a hexadecimal number. So, this is an hexadecimal number 2, sorry, I will take decimal first, then binary I will go. Let me take decimal first, then we will go for binary. As I said you there, if it is 3, I will put 3 there. If it is 16, hexadecimal number system, I will put R16. Now, the position 0, 1, 2 plus C means 12 into 16 to the power 1, again C 12, 16 to the power 0 plus A means 10, 16 to the power minus 1. Do it. Number you will get 7, 6, 8, 1, 9, 2, 12, 0.625, and finally 972.625 in decimal, using the same formula what we have used there. How can we can justify this? If I take this number divided by 16, remainder will come, again divide it, again one remainder will come there, remainders will come C, C and 3. So, from bottom to top I will go 3, C and C. Similarly, I will take 0.625 and multiply with 16. I will get the carries there. A only means 110 I will get, nothing will come after that. Okay. Now, let us move for hexadecimal to binary. Again the same idea like octal system. In octal we had 8 options. By using only 2 things 0 and 1 we had to represent 8 levels. Now, here we have to represent 16 levels. So, 2 to the power of 4, that means I need 4 bits. This much only is the difference, nothing else. So, take the same route. If I want to represent this 3 in 4 bits, what should I? C. C means 12. 1 1 0 0. Again, then 1 0 1 0 in the binary system. Other way, if it is in binary, then if I want to go to hexadecimal, I will again make them bunch of 4 and convert them to hexadecimal number. Okay. So, this way the hexadecimal numbers and octal numbers are very much useful in our computers there in digital systems. Okay. Let us move for actual digital systems or logic gates to use for digital systems. I will take few basic laws at the beginning, then I will go to the actual topic. I think maybe few things are known to you. This, are these known? Few people know, few people may not know. If it is not, please take it. These are the pure algebra what we do for binary numbers there, where A and B they can take either 0 or 1. Okay. Now, if A and B they are or to one another, or A or B, that is same result you will get if you take B or A, no difference is there in between. Similarly, A and B and B and A and B and B and A means logic n I am saying are same. Okay. Similarly, here if you make this change A or B or C or A or B or C, both are same. A and B and C or A and B and C are same, or you will say A and B or C is again same as A and B odd with B, A and C. Okay. So, now few things are known, few are not. Without going for any confusion there, I will be using the known gates there. In that I will be introducing few other gates which may not be known to you. Along with that, I will follow a track there where you will see at the end I have some intention to do that, or the approach what I will take here for discussing this logic gates here it has some reason. Logic gates I am discussing here, small things also I will take in between, starting from the idea of basic OR gate, AND gate and NOT gate, use for which I consider just it is known to you, beyond that you do not know much. With that idea we will proceed now. Okay. Say somebody has asked you, make one digital system which will have an output y. What y it is? Either it is 0 or 1, because we are in the digital system and we understand only 1 and 0. This in terms of say 3 variables. Okay, let me take the expression first. A bar, B bar, C bar plus A bar, B, C bar, A, B bar, C bar plus A, B, C bar. This equation I will continue with till next class. I will keep this equation. Say one digital system, by using digital logic gates, I have to devise the system which have the logic like this. What does it mean? It means if I have 3 inputs A, B and C, which can have their value either 0 or 1. If I take inversion of it, means if I pass this A through a NOT gate, I will get A bar. That means what? If I get the truth table there, A and output is Z there. If it is 0, it is 1. If it is 1, it is 0. Okay. So, this A bar is that one. Similarly, if I go for B bar or C bar, there is nothing but NOT operation of the actual variable A, B and C. Okay. Now, if I do OR operation, in that case I need to use 2 gates there, 2 inputs there, say A and B are the 2 inputs at least. In that Z is the output there. What are the options for A and B? 0, 0, 0, 1, 1, 0, 1, 1. So, since you are saying OR, then the logic comes like this, either A or B. If it is high, then only the output is high there. So, you put it this way, okay, which is symbolized as this plus sign here. And if these are as a product presented here, those are ANDing. If I have 2 variables A and B and Z is the output, then output will be high only if A and B are high. So, it is 0, 0, 0 and 1. So, I wrote this Z as A, B, means A and B it is, just like a product operation. Similarly, here if it is Z, A or B, that is represented as A or B in this fashion. Just like here we represented A as A bar. Now, in place of 2 variables, if I put 3 variables there, A, B, C, so Z will become A and B and C. This is that. But only thing is that prior to go for ANDing, individually they passed through a NOT gate. Understanding is like this. AND operation is there for not A, not B and not C. Similarly, for this, AND operation is there between A, B, C, but with not A, not C and B. Then those 2 are OR together. Again, if I consider these 2 are like that and OR together, then you will get some expression for these 2 and some for these 2, then again you have made OR operation. So, from 2 input to 3 input we have gone. Okay. Let us implement this circuit directly in terms of logic, gate, AND, OR and NOT, please. with your known idea, if I proceed with this, what I will do? First, you will see here that 3 AND gates are required of input 3. So, let me put 3 AND gates like this, which has inputs. For first, it is A bar, B bar, C bar. So, first part is found there as an output of this one. Similarly, for the second part, what I will do? A bar, B, then C bar. Oh, sorry, 4 are there. A, B bar, C bar. A, B, C bar. These 4 outputs are there because 4 terms are there available. Now, all are OR together. So, if I want to use only single OR gate, so 4 input OR gate is sufficient. So, I will put them together to achieve the Y. Okay. Now, if you say I have the variable A, B and C, then I will ask you draw 3 sources A, B and C. Then you give them to them, like A I want, A bar I want here, put a NOT gate there. So, this A has got as not A. Okay. Here, then done. Similarly, here if I want not A, I can take from here also, or I may use another NOT gate, and since here I am saying it is B, directly I will be drawing from here. Okay. So, you complete the thing, C bar like this. Okay. Now, see how many NOT gates do I need here? 1, 2, 3, 4, 5, 6, 7, 8. At least 8 NOT gates are required there, and 4 AND gates are required there to address this 4 different terms of AND operation, and then finally 1 OR gate to make them together to get the final expression. Okay. Now, people try for bigger circuits actually. They will question, is it the only way we achieve this Y? If I say this Y I want to achieve, to get it you have to now make one truth table there, where you will put A, B, C as 3 inputs and Y as output. Now, 8 combinations will be there, and for that this individual things will be coming there with that combination of A, B and C. You have to find out what Y should come there for different combination of A and B and C. Okay. So, finally, it is asking you if A, B and C are the 3 inputs, A bar and B bar and C bar, if they go 1, this term also goes 1, this term also goes 1, this term also goes 1, then the output will be 1. This is all it is saying. If it is not, then it is 0. Okay. So, to achieve that only, if I like to reduce the number of gates which are used there, that may be the better approach or cost effective. Okay. So, to do so, the laws which we have taken there at the beginning, those can be used for further manipulation of this equation. Let us check that. And one thing I should tell you, that it is not about only to minimize the number of gates, it may be the availability of the gates by which you want to implement a digital system or logic system there. There also may come some restriction there, but like you want AND operation, but you do not have AND gates. In that case also these are helpful there. So, I will not say only simplification, but I will say another implementation of the same thing. Why I am implementing in another way? Say we tell it as 1. Now, this y is again taken there. Now, I will put one observation there. I am saying for all the 4 terms C bar is available. So, let me take that C bar outside. Like this. The loss which we have taken there, it supports this. Okay. So, if it is like this, then from here itself you can observe there that it does not require any 3 input gates, only 2 input gates are enough. Okay. Why? Because these are all 2 input, then I will make ORing for individual maybe, then I will make them together as a single one, then ending with another single variable, done. Okay. Whatever way you like, you just realize it. Here I want something more to put into it. See here, this particular quantity, one is A bar B plus B bar, A bar B and plus or A B bar. If I ask you to find the truth table for this, please find out the truth table for this part. What we will get? 0 0 0 1 1 0 1 1. In that case, where will be the output 1? Only for A, if A bar and A is 0 and B is 1, then only this term exists. Otherwise, it is 1. Otherwise, it is 0. Similarly, here, if A and B bar means B it is 0 and A is 1, then this exists. So, if I take them together and find its output there, so I will get 1 1 here and 0 here. But for OR gate, I was getting 1 1 for all these 3, but not here. This kind of gates are also available to us, which are called exclusive OR gate. Why it is called exclusive? Because it is output is 1 only if exclusively A and B are high. If both are high, still it is 0, which is different from the OR gate. Okay. And gate level representation is like OR, but symbol wise little different there. So, this is the exclusive OR. Okay. So, if I implement this part in terms of exclusive OR, say that a gate is available to me, that can reduce this part. Okay. Then one AND gate, another AND gate, then finally another AND gate. Please implement it quickly. Let us see. Sorry. What is the input of exclusive OR gate? What is the input to exclusive OR gate? Here for the AND gate I have used an A bar B bar. I could put not gate there. Say A bar B bar to the AND gate. For this A B to get these 2 terms. Now for this exclusive OR, what should I put? A and B there. Okay. Now, these are found as 3 quantity there which should be ORed. One quantity is still there who is C bar. So, you can easily use one NOT gate. For the C terminal, you put one NOT gate and finally put here to make it ANDing to get the Y. Since you already know NOT and AND, let me use another gate there for it. Which is called NAND gate. NAND means not AND. If I say it is AND, few relations which may be useful for you later case. Say you are making AND of 2. So, it will become A and B. If it is 0, then output is 0 always. So, 2 input NAND gate is available, AND gate is available to you. 2 input AND gate is available to you with 2 inputs A and B say. Now, B is also A, means both the inputs are A. What will be the output? A. If one is A, another is 1, output A. If one is 0, another is A, 0. Okay. Now, if I say, if I put it 1 here of one input to the AND gate, it does not do anything to the circuit. It replicates the input to the output directly. Can I say this way? Similarly, I will say other way here. If I put one terminal 0, whatever you put at the input, output will be always 0. Okay. Another thing, if at the input both the terminals are used for the same supply, then output will be same A. Okay. This is nothing new, only AND operation we are looking into different manner. Now, in this it is said it is not AND but NAND. So, it is just not of the AND operation, this much only. Okay. Now, so in the truth table if you find the Y, the final output was 1 for 0 0 it is 0, 0 1 0 and finally 1 1 1. Now, it is inverted. For all remaining 3 it is 1 and last one is 0, this much only. Now, since say I have only a NAND gate there, no NOT gate. So, for that I am taking this C and that is I am applying to the both terminals and I am passing through it to the NAND gate, so that I get C bar here. Okay. So, this C bar and the remaining part has got AND and finally, this is the same expression what we started with. Repeatedly I am saying I do not have any intention of doing in another way. It is just to show you the implementation of different kind of gates there in the circuitry. And one thing you are automatically seeing there, how the simplification is getting made in between. There is one observation. Okay. But my purpose is to float different kind of gates which are there, taking the ideas which we have for other for the laws which we discussed at the beginning. Before I go for the implementation 2, let me take one theorem which is very much popular, which is called De Morgan's theorem. It is like if you have 2 input OR, but you want to implement it by AND gates only. This theorem is very much helpful to you. How? Because it says, theorem says that if you take not of A or B, it is same like not A and not B. Okay. Similarly, if you take 2 input and not of it, it will be same as A or A naught or B naught. Fine. So, this is the theorem says by De Morgan. Let us use this theorem in our this expression, either this or this here, to implement, so that we extend this in another form. Can I represent this in this form, that A bar B as A bar B bar with De Morgan's theorem? This was not there in ending, but I have only OR operation. Maybe for this I need another gate there, which is not OR but NOR. Okay. So, that way the modifications can be made in between. Another way, if you would like to make this also changed, like A B not of not, again A B, in that you could make it like this, A B not, or no, A bar B, A bar or B bar, then again bar, but OR operation. Okay. So, this way modifications are again allowed to you. After doing so, whatever be the simplification it is coming there, you can proceed for that. But finally, quickly I will go for another implementation, which is say implementation 3. In this, let me take common A bar, which is found same for this two. A bar B bar plus B plus A B bar plus B, and finally C bar. See here, this is very important. If one bit is in 1, then the another one is at 0. See, always it is becoming 1 plus 1 or 0. So, finally outcome is 1 only. So, I can remove this part. So, it is becoming A or A bar or A, again it is 1. So, it is C bar. Whatever you have done till now, they would not be required to do actually at all. The output is nothing but C bar only. Is not it? So, if we would write this in a truth table, in that it would be better to see that what will be the best way to represent that one. But always it is not possible to make that observation, that by which we will be able to say which is the simplified one. Mathematically also we can do that work. So, that will be taken in the next class with the reference of the same circuitry. Okay? Thank you.